S1 Lesson 4, Probability, Conditional Probability. Before you start, it would help if you've got a printout of the presentation slides so you can annotate any of your own notes as we go through. And a pen, paper and calculator will definitely be handy as you should be taking part in the video. So just an overview quickly of the S1 topics. We're still on probability and looking at conditional probability today, and we have some other topics there to cover later on. So, conditional probability, what is it? Sometimes the probability of an event B depends on the outcome of a previous event. So for example, probability B given A, this is the same as saying probability that B occurs given that A has already occurred. Okay, so what we can say is that this little line in between B and A is just notation for the word given. So this is B given that A has happened. Let's have a look at an example. A fair six-sided dice is rolled. What is the probability that the number rolled is even, given that it is prime? Okay, so we've seen how to use a Venn diagram and organise events using a Venn diagram. If we say the event A is even and the event B is prime, we can organise the outcomes of rolling a dice into our Venn diagram. So the even numbers, 2 is prime, so that's going to go in the middle where it's even and prime. 4 is not prime, so it's just going to go in the A section. 6 is not prime, so it's going to go in the A section. Considering event B, so that is having prime numbers, 1 is not prime, 2 is prime and is already written and is in the intersection because it's also even. 3 is prime and 5 is prime. The remaining numbers is just the number 1. So, what happens in this question? We've said, what is the probability that the number rolled is even given that it is prime? So what I'm saying is, probability of A given B. So what I'm actually doing here is, if I just use a highlighter pen, we're being told, because it's prime, it must only be one of these 3 possible outcomes. So that tells me straight away that the probability must be out of 3, because that is the total possible outcomes, because I know that it's prime. So the outcomes has been reduced from 6 possible outcomes to 3 possible outcomes. How many of those outcomes are even? Well, it's just 1, so we get a probability of a third. Okay, so here's our definition of conditional probability. Here's a Venn diagram. If you consider the probability of B given A, again reverting to the highlighter, if I've been told that the event A has occurred, then what I know is that only this possible area of the Venn diagram, which has actually been extracted below here, is actually possible. And so the part that is in B, I'll highlight now in the lower diagram, so that is going to be this small section here out of the probability of A. Now, the whole probability, this green section, that is probability of A, and this yellow section here, which is the possible things that could happen out of A, is probability of A intersect B. And so hence we get this definition that probability of B given A is the probability of the intersect of the 2 events over the probability of the event that has already happened. So let's have a look at a different example. In a small sixth form of 50 students, maths and English are the 2 most popular subjects. 30 students are studying maths, 25 are studying English, 10 students are studying maths and English. Find the probability that a student studies maths given that he or she studies English. So what we know is, let's call A is maths and B we're going to say is English. Starting with the intersection, what we know is that 10 students are studying both maths and English. Looking at the maths students, There are 30 students studying maths, so there must be a remainder of 20 in the rest of that section. There are 25 students studying English, so there must be a remainder of 15 to make that whole section add up to 25. And there are a total of 50 students, so what we've already accounted for is 45 of the students, so there's 5 students left. Now what we wanted to find was the probability that the student studies maths, so probability of A, given that it studies English, so probability of A given B. Now I don't tend to do this with a formula. Let's just highlight the area which is relevant to this question at the moment. So what we know is that they study English. So if they study English, what we're looking at are these 25 students inside of B. I can ignore the other 25 students. Okay, so in that case, I know my probability is out of 25. And then, so looking at the probability of whether they study maths, given that they're in this small section of students, that is then the following area, which is just this section here, which is the 10 students, so 10 out of 25. And again, as a matter of interest, this whole area that I've highlighted in green, that was a probability of B, so the probability of that event that has happened, and that probability on the top is the intersect of A and B. Okay, hope that all makes sense so far. So here's one for you to try. 25 interviews were undertaken by a sports centre to research how people kept fit. Of the 11 men interviewed, 7 preferred team sports to working out in a gym, 8 women preferred working out at a gym to team sports. Given that a person who prefers working out in a gym is chosen at random, what is the probability that this is a woman? So really need to be careful with how you organise this and what you do. But what I want you to do at this point in time is I'd like to pause the video and have a go. So pause the video now. Okay, so welcome back. Let's have a look at this question. So the information was about men and women. So let's just say F represents women. Okay, and so following that, we also have G, which is going to represent the gym. Now, in the information given, 8 women preferred working out at the gym to team sports. So 8 women and gym goes in the middle there. There was 11 men, so the total outside of the female must add up to 11, and those 11 men interviewed 7 preferred team sports to working out in a gym. So if there are 11 men, so F complement in that case is 11, and so we're told that 7 preferred team sports, so what we have is probability of F complement and G complement equals 7. So that's the area on the outside here. What that leaves is 4 men who do prefer the gym, which goes inside there. And finally, we have 15, 19, so there's a total of 19 people in there, so the number of females in this last section must be 6. So slightly trickier there, because we had to work out that actually that we're inside this area was females, and so how the information was actually provided. Now the question asks, given that the person who prefers working out in a gym is chosen at random, what is the probability that it's a woman? So again, the section I'm looking at here, the person prefers the gym. So what we're saying, going back to our notation, probability that it is female, given it is the gym. Well, we know that this is going to be out of 12 because there's the number of people who prefer working in the gym is 12. And then we have this little section here, this is the females. And so we have 8 out of 12 females who prefer this. And again, just notice that what I've used this section here is probability of F intersect G, and the whole yellow section which I've highlighted is the probability of G that event that's happened. Okay, so it's important linking it backwards and forwards to the formula as well as just reading from the diagram. Okay, so these contextualized problems are okay to get a feel for things, but really what's likely to happen in the S1 exam is that you don't get a contextualized problem, you get something like as follows. Given that the probability of A is 0.4, the probability of B is 0.3, and the probability of A given B is 1/3, find the probability of A intersect B, A complement intersect B complement, B given A, and A complement given B complement. Okay, so starting off, just a reminder, we know that the probability of A is 0.4, probability of B equals 0.3, and the probability of A given B equals 1/3. So, I mean, I'll use the formula here, probability A given B equals probability of A intersect B over probability of B. So I can rearrange this and actually find that probability of A intersect B this can be found by doing the probability of A given B times the probability of B. I'm just going to times this original equation both sides by the probability of B. So what we get is we get 1/3 times 0.3, which gives us an answer of 0.1. So I know the probability of A intersect B is 0.1. I can fill that in on my Venn diagram now. So that's 0.1. I can fill in the rest of A. That would be 0.3 because these two add up to total 0.4. I can fill in the rest of B. That will add up to 0.3. So that's 0.2. In total, in all these sections, I've got 0.6. So on the outside, I'm going to have 0.4. Now, probability, moving on, of A complement intersect B complement. Well, A complement is outside of A. And I also want B complement, so it's going to be outside of B as well. So it's going to be 0.4. Probability of B given that is in A. So what I'm going to be working with is this probability of A. So that is over 0.4. And then the probability is in B is this bit here out of the 0.4. So 0.1. And so I can give that answer as 1/4. Probability of A complement given B complement. So B complement is outside of B, so that is the 0.3 and the 0.4. That's outside of B. So what I'm looking at is a probability out of 0.7. And the probability is not in A is going to be outside of A. So out of these two sections, the 0.3 and the 0.4, it's going to be outside of A, so it's going to be the 0.4, which equals 4/7. It's worth noting again that what we calculated here was the probability of A intersect B, so that was my 0.1, over the probability of the event that's happened, so A. It's also worth noting for the second one, we did the probability of A intersect B, A complement intersect B complement, so 0.4 on the top here, and that was out of the probability over the probability of B complement, the event that's already been given. Okay. Well, I hope that all made sense because now it's your turn to try. So here's one for you. Given that the probability of A is 0.5, probability of B is 0.7, and probability of B complement given A complement equals 0.2, find the following. So at this point, pause the video. Okay, welcome back. So let's have a look at the answers to this. What we're given is we know that probability of A equals 0.6, probability of B equals 0.7, and probability of B complement given A complement equals 0.2. Okay, the thing to note here is that if you've got the probability of A, you've actually got the probability of A complement, because A and A complement add up to 1, so that's 0.4. If you've got probability of B, then you've also got probability of B complement. That would be add up to 1, so that's going to have to be 0.3. So when I have probability of B complement, A complement, what I can do is I can use that to find intersect of A complement, B complement. So I can use the conditional probability formula so that I can find that the probability of A complement intersect B complement equals probability of B complement given A complement times the probability of A complement. So we get 0.2 times 0.4, which equals 0.08. So A complement intersect B complement, that's the area outside of our Venn diagram. And this really is quite a challenging question. So I've got that area outside the Venn diagram. What I know then inside here, my probability of A union B, that must be 1 minus the 0.08, so that's 0.92. And so we can use the addition formula then to find probability of A intersect B, because that's the probability of A plus the probability of B minus the probability of A union B. And so the questions have led you through this because part A wanted you to get A intersect B, part B wanted you to find part A wanted you to get A complement intersect B complement, part B wants you to find the intersect. So we get the intersect, that's going to be 0.6 plus 0.7 minus 0.92. So when we work through that, we get an answer 1.3 take away 0.92 is 0.38. And so I can start to fill in the rest of the Venn diagram. So given that there's 0.38 in the middle here, 0.22 must fill up the rest of A, and 0.32 must fill up the rest of B. And so now at this point we have a complete Venn diagram. We can find the probability of A complement given B complement, because we already had B complement given A complement. So this is, well, this is going to be out of, first of all, we're told it's B complement, so outside of B is 0.3, so this is going to be a probability out of 0.3. And then we want it to be not A, so that's going to be this section out here, which is a 0.08. So we get 8 over 30, which will cancel to 4 over 15. Finally, probability of A given B. Well, we know it's in B, so that means I'll get a probability out of 0.7. And then the part that is in A is 0.38. And if we cancel that down and get it to a sensible fraction, we get 19 over 35. Okay, I hope that all made sense. Some fairly challenging conditional probability questions there. Okay, so conditional probability plays an important part in our next section. Tree diagrams. So tree diagrams are often used to represent successive events, and so in these cases conditional probability occurs. And in a traditional case of this is that you meet at GCSE probability, which we visited in the essential knowledge, is things like choosing 2 counters from a bag. So let's have a look at an example. We're told Ruth drives her car to work, provided she can get it to start. When she remembers to put the car in the garage the night before, it starts the morning with a probability of 0.95. When she forgets to put the car away, it starts the next morning with a probability of 0.75. She remembers to put the car in the garage 90% of the time. So what is the probability that Ruth is able to drive her car to work on a randomly chosen day? And what is the probability she put it in the garage, given that she's able to drive to work? Okay, so the important part of these questions is actually organising yourself to understand the successive events. The first event is, does it go in the garage? So we're going to have probability of it going in the garage, and it said that she remembers 90% of the time, so that we're going to write that as a decimal, as 0.9. And probability, she doesn't put it in the garage, so I'm going to use G complement. It's the most sensible to use one letter and use the complement. The second stage is, does it start? Now the information in the question tells us that if she's put it in the garage, it starts 95% of the time. So this is conditional probability that it will start given that it's gone in the garage, and that's 0.95. That means the probability that it won't start, so S complement given that it has gone in the garage, is 0.05. The other piece of information we're given is that we are told that the probability of it starting, if it has gone in the garage, is 0.75. So probability of it starting, given that it didn't go in the garage, equals 0.75. The probability of it not starting, given that it didn't go in the garage, is 0.25. So notice here a slight change in the notation because I'm saying the probability of it starting given that it was in the garage. Before we might just put this as start, not start, start, not start. But actually technically speaking these are conditional probabilities. And so you can see we then multiply across the branches and that kind of links to that idea that we've used earlier. So probability that it went in the garage and it started is 0.9 times 0.95, which gives us an answer of 0.855. Probability of it going in the garage and not starting is 0.9 times 0.05, and so we get an answer of 0.045. Probability of it not going in the garage and starting is 0.1 times 0.75, so we get 0.075. And then the probability of it not going in the garage and then not starting is 0.1 times 0.25, which is 0.025. Now, we had two questions to answer. What is the probability that Ruth is able to drive her car to work the next day? So what we're looking at is actually which ones are starting. So this probability here at the top is starting, and this outcome here, the car starts. So the probability that the car starts is 0.855 plus 0.075. And so when I add these two together, we get a probability of 0.93. So she can drive to work 0.93 with a probability of 0.93. Next question says, what is the probability she put the car in a garage given that she is able to drive to work? So this is the important learning for the tree diagram. This is all that's new really for A-level maths regarding the tree diagram. Okay, understand the question. It's saying what's the probability that she put it in the garage. So probability of it going in the garage given that it started. And at this point, this is where using the formula really is useful, because what I know is the probability of that is the probability of it going in the garage and starting over the probability of it starting. So that is 0.855 over 0.93. And when we simplify that, what we come to is the fraction 57 over 62. And it's perfectly fine to leave it as that fraction. Now, tips on using tree diagrams. A lot of people don't really want to, will probably fill out the first two branches, but probably leave out these end probabilities. If you're just getting used to the habit of completely doing these tree diagrams, making sure you identify, first of all, so I'd start off by identifying what are the successive events. Second of all, then start to fill in your branches. If you can use the correct conditional probability notation, it's a good idea too. It will help you have your understanding of what's happening. Finally, make sure you do complete the end branches. Even if you can't answer the question after that point, you'll actually get chunks of the method marks for parts of this end probability. In fact, this probability of starting, you'll probably only get 1 mark for the answer at the end. The rest of the method marks, etc., all come from the tree diagram itself. Okay. Finally, then use conditional probability. It's really important that we use this conditional probability formula here because it will make life easier to identify what probability is used in conjunction with what other probability. Okay, well I hope that all made sense because it's now time for you to try one. A factory has 3 machines making paper clips. Machine A produces 40% of the total output, machine B produces 35% of the total output, and machine C produces 25% of the total output. It is known that 2% of the paper clips produced by machine A are defective, 2.5% produced by machine B are defective, and 0.5% produced by machine C are defective. A paper clip is selected at random from the total output. A, calculate the probability it's defective. B, given that it's defective, find the probability that it was produced by machine A. Okay, so you pause the video and try this out yourself. Okay, welcome back. So let's have a look at this question. So 2 stages again. First stage is going to be the machine. We're going to have to use some different notation for this because we've got 3 machines. I've got machine A. Machine A produces 40% of the clips, so I've got 0.4 for machine A. We have machine B. Machine B produces 35% of the paper clips, so we've got a probability of 0.35, and machine C produces 25% of the paper clips. Let's just make that clear that that is a C. Okay. Okay. So then what we're also told is that in machine A, 2.5% are defective. So this is whether the second step is, are they defective? Okay, so probability of it being defective, given that it's from A, 2.5% is 0.025. Probability that it's not defective, given that it comes from A, is in that case 0.975. Probability that it's defective, given that it comes from machine B. Well, that is given as, just flip back a second, 0.5% of the time. Sorry, let's go back. I've misread that question there. So actually it's 2% of the time for machine A and 2.5% of the time for machine B. So 0.025. So the probability is not defective given that it comes from machine B is 0.975. And then finally, probability is it being defective given it comes from machine C is 0.005 because it's 0.5%, and so the probability it's not defective given it comes from machine C is 0.995. At this opportunity, I complete the end branches, so probability of it being from A and defective will be 0.008. Probability of A and not defective is going to be 0.0. It's going to be 0.392. Let's just rub that out a second. So 0.392. Okay, so probability it's from B and defective. So we get 0.35 times 0.025 is 0.00875. Probability of it being from B and not defective equals, and let's just clarify this up here, so apologies, a couple of errors in my notation there, is going to be 0.35 times 0.975, which comes up as 0.34125. Finally, probability of it coming from C and being defective, 0.25 times 0.05 gives me 0.00125, and finally probability of C and it not being defective comes out as 0.25 times 0.995, which gives us an answer of 0.24875. Now, in all likeliness, you're not really likely to work with probabilities like this in the exam, but it's exactly the same regardless. Now, what we was asked to do was find the probability of it being defective. So I look at my end branches and I just identify where have I got defective outcomes, and so the top one is defective, third one down is defective, and the fifth one down is defective. So probability of it being defective is given as 0.008 plus 0.00875 plus 0.00125. Okay, so just using the OR rule, just like we do in GCSE. So if I add these probabilities together, okay, and what we get is an answer of 0.0018. 0.018, apologies. Finally, the last question said, given that the paperclip is deflective, find the probability that it was produced by machine A. So again, this is where the conditional probability formula comes in real useful. So I'm saying the probability that it comes from machine A, given it's defective. So I get the probability of A intersect D. So probability it's A came from A and is defective over the probability it's defective. So I get 0.008 over 0.018. And so when I simplify this as a fraction, we get an answer of 4/9. Okay, so I hope that all made sense. Now, finally, we move on to Bayes' theorem. I've decided to include Bayes' theorem just to be complete, but really we've already been using Bayes' theorem. If you've got, what Bayes' theorem says is if you've got a set of mutually exclusive events that form the entire sample space, so for example, what we could be talking about here is rolling a dice, so we'd have 1, 2, 3, 4, 5, 6, they are mutually exclusive events that form that sample space, and if we let B be any event from that sample space, then Bayes' theorem states that the probability of B happening is the probability of B given A times the probability of A plus the probability of B given A, the second outcome, times the probability of A. Now essentially what we've got here, and just explain this to yourself, is each one of these parts of our theorem that we are summing together is like the end probability on our tree diagram, because this actually represents probability of A1 intersect B. And so we get probability of A2 intersect B, and so we get the probability of A3 intersect B, and so on. So probability plus probability of AN intersect B. Okay, so what this is saying is actually, if we want to find this probability, and this is exactly what we've done if we go back to our previous example, Bayes' theorem. So here's where I've used Bayes' theorem. So I've said the probability of it being defective is probability of A times the probability of D times A, D given A. Probability of it being defective is probability of B times probability of it being defective given it's from B. and so on. And so these were my end probabilities, and they were what I summed together. So this can be used if you are incredibly organized and you can really visualize what's happening. This can be used to avoid using a tree diagram. I'm going to do one example doing this. Personally, I don't choose to use Bayes Theorem. I prefer to have a tree diagram and kind of space it all out because I'm a visual learner and I want to see that. But you might find this more useful. So we've got Anne has a fair coin and a double-headed coin. She chooses one at random and tosses it. The coin shows heads. Find the probability that she tossed a double-headed coin. Okay, so let's have a look at how this is worked out then. So what we're going to say is we've got a fair coin and a double-headed coin. So let's say fair probability of picking a fair coin is P of F. That's going to be 0.5 because it's 1 out of 2 coins. And then we're going to choose one at random and we're going to toss it. So if we've got probability, I'm just trying to think how we could use notation here, probability of a head. Okay, so this is all going to depend now, so it's not very good notation, this example. So what we're saying is probability of a head. So the first thing that could happen is I could say, okay, pick the fair coin, and then I have to multiply this by the probability that I get a head, given that it's the fair coin. And then the other thing that can happen is I can say, okay, well, probability that I didn't get the fair coin, and then I have to multiply this by the probability of a head, given that I didn't have the fair coin. So probability of the fair coin was 0.5. Probability of a head given the fair coin is also 0.5. Plus probability of not getting a fair coin is 0.5 times the probability of getting a head because it's not a fair coin. Well, we know it's double-headed, so it's a probability of 1. So what we get is 0.25 plus 0.5 is equal to 0.75. Okay, so I mean, it can be quicker. It requires a real analytical understanding of what is happening in the situation, and you have to make sure that you really do understand what's happening in the situation because you have to list absolutely every outcome. The advantage of using the tree diagram, and if we quickly look at the tree diagram, is that it represents and it gives you all the outcomes. So here was my probability of a fair coin. That was 0.5. Probability of an unfair coin, 0.5. And then so I had up here probability of a head, given that it was unfair, given it was fair, sorry, was 0.5. Probability of not a head, given it was a fair, is 0.5. And then finally, probability of a head, given that it was unfair, was equal to 1. And so my end probability is probability of fair and a head. 0.5 times 0.5 was 0.25. Probability of fair and not a head, 0.5 times 0.5, which is 0.25. And probability of a fair coin, not a fair coin, and a head is 0.5 times 1, which is 0.5. And so all we did was we said, okay, probability of a head. Okay, and the bit that I haven't, all that the tree diagram does really is organise you to make sure you don't miss any outcomes. So probability of getting a head was the top outcome and the bottom outcome, which gives me 0.5 plus 0.75, plus 0.25, which comes out as 0.75. So it's exactly the same answer, but we can use a diagram to organise ourselves, and perhaps requires a little less thinking and is a little less of a risk because you can ensure that you cover all the outcomes and don't miss anything. Okay, well I hope that all made sense and you understood conditional probability. All that's left to say is now for you to go on, have a try at a conditional probability exercise, build up your confidence, make sure that you're able to use conditional probability with Venn diagrams and with tree diagrams. Once you feel confident with the conditional probability exercise, have a go at assessment 4, conditional probability. Okay, well I hope you enjoyed that and it all made sense.